Today's lecture is Chapter 4, Geologic Structures. Just a reminder that in Chapter 3, we studied something called plate tectonics. In plate tectonics, we studied the movement of the plates and how the Earth was shaped. Now, we are going to go deeper into these plates and to study the shape of these plates. Are they leveled? Are they inclined? What happens to them when they collide with each other and something like this? To study geologic structures, we have to define two main groups: primary and secondary tectonic structures, or primary or non-tectonic structures, and secondary or tectonic structures. So we have tectonic or non-tectonic or tectonic. What is tectonic? It deals with what we have studied in this chapter, plate tectonics. So tectonic structures are the structures that are affected by the movement of the plates, similar to earthquakes and volcanoes and something like this. But non-tectonic structures, these are the primary structures. They were formed at the beginning of the formation of the Earth. So they were formed very, very long time ago, and they were affected by the forces that shaped the Earth. But later, after millions of years, due to the mutual interaction between the plates and other forces around them, some modifications happened to these structures. This is really what we are going to study in this chapter. We are going to study something called faults, folds, and fractures. So we are not going now to concentrate on the formation of the plates. The formation of the plates, we studied it more or less when we were studying plate tectonics. Now, after the formation of the plates were modified with time. So they are not in the same shape as they were formed at the beginning of the creation. They have changed. So how they changed and why they change, this is what we are going to discuss. What is the importance of this to us? Because we deal with buildings, we are engineers. We need to put our buildings on top of the ground. So to do this, we have to do some site investigation to discover the land or the soil beneath us. Are we going to do millions of boreholes and dig everywhere to discover? No, we just dig sample boreholes. So how can we do this? We do few numbers of boreholes, and we have to anticipate what is between them. If we don't know what to expect, then we will not be able to anticipate correctly. So that's why we are going in this chapter to study secondary or tectonic structures. Let's start with this. There is something called, now we are going to add to your file of terms, geological terms. There is something called bedding or stratification. What is bedding or what is stratification? We know that layers are formed, soil is formed as layers on top of each other. Are all layers the same? No, they are different. So there should be a line of separation between one layer and the layer on top of it. This line of separation is called bedding. So if I look at this photo, I have here lots of layers, here lots of layers. The separation between each layer and the other is called a bedding. So a bedding is the line of separation between any different layers. Any two types of soil that are different, then the line of separation is called a bedding, because each layer represents a period of time. During this period of time, soil were sedimented in a different way. Then later, time changes, and the type of formation has changed. So another new type of layer starts to sediment at this location, so there will be a separation line. So if I look here, I will find lots of lines. All of these lines are called bedding. But if you look at these lines, they are horizontal. So we can say that this is horizontal beds. It means that the bedding are horizontal. Are they always horizontal? No, this is a special type. This is really it should be the normal type, but there are many other types of beddings. So the first type is called horizontal beds. The second type is called graded beds. What is graded beds? It means that if you look at this photo, you will find that there are lots of lines, but if you look at at this line, you find that on top of it you have coarse material, and if you go up, you find that this coarse material starts to be smaller in size till it reaches very fine material. So all of this layer, it starts with big particles, and then the particles start to diminish in size till it is very fine particles. And once it reaches this top, it changes again into another layer, another bed, where big particles are sedimented, followed by smaller, and so on. So this is a presentation of the shape. This is the bedding plane, and it starts with big size, then smaller till it is very fine, and then it repeats again. So this is called graded beds. Another type is called cross beds. Look at this. If you concentrate, you will find that there is a tendency for layers going in this direction, and there is another layers going in this direction. So if you look at the presentation, these are the main stratifications, these horizontal ones. And these nearly vertical are another type of beds. So let's start with this layer, this bedding plate. Here, or this bedding plane, this is the bed, and then layers come and are sedimented nearly vertical on top of this layer. Then, once it is finished, a new bed is formed so that the next layer are all nearly vertical on top of it. So it is another type of formation of layer. Of course, the formation of the layer depends on many things, on the type of the material, on the environment around the material. Are there rains, heavy rains, or not? Wind, everything around us help in the shape of the layers that are formed. Of course, we are speaking about millions of years. We are not speaking about few years. It means between this layer and this layer, there may be 1 or 2 million years to be formed, and so on. So this is another type called the crossbeds. I will tell you later why we are discussing this. This is very important for us, but we will discuss it at the end of the lecture. Look at this photo. This is a layer. Of course, it is rock. It is a rock layer. Do you consider or do you think that this layer was formed at the beginning in this shape, this curved shape? How can rock be formed in a curved shape? Usually, rock starts with fine material on top of each other. Then, because of high pressure and high temperature, it changes from being fine particles into rock masses. This is the normal shape. But the rock mass will be a layer. It will be one layer. Usually it would be horizontal. Why this layer changed to be curved? What is what do you think would be the reason for rock to be curved? Can you think of anything that would cause rock to be curved? A rock layer, a horizontal rock layer, can it be curved? Any one of you would think of something? There should be some kind of external forces. Imagine that you have a plate, and this plate, you start compressing this plate from the edges. What would happen? Did you study something called buckling in structure or not yet? Not yet. If I have a ruler, and then I compress the ruler, plastic ruler, and I compress the ruler from both sides, what will happen? It will buckle. It will be curved in shape. This is normal for any material. Rock is a material. So if I have a layer of rock and I compress it from both sides, what would happen? It would either curve upward or curve downward. So this type of rock has been subjected to compression from both sides, resulting in this shape. Another shape, it's called rock outcrop. What is rock outcrop? It's the same shape that you are seeing in this photo. You have this, this is the ground level, and then there is something emerging out of the soil, of the soil. What is this? These are layers of rock. These layers of rock are inclined. What happened to them? They were below the ground. They may be kilometers below the ground. But what happened? With time, these layers were ejected on top of the earth. Why? Because of some kind of forces below. Now we go into two definitions, very important definitions for geology. Because if I tell you that now we know that we have layers of rock, and these layers of rock may be horizontal, may be inclined in any direction. So to define them correctly, I have to say to give them some engineering angles so that I can measure this inclination of these rocks. Are they inclined in which directions? Of course, we are speaking about something in the 3 dimension. So we have two things to discuss: dip and strike. These are very important for geology. This is a sedimentary rock. You know, sedimentary rock means that the rock was formed by the sedimentation of material on top of the ground. So if I have these layers of sedimentary rock, they are inclined. but inclined in which degree? So, or in what degree? So we have two angles that we should give to this rock. The first angle is called the dip. If this is the sedimentary layer, this layer will have an angle with the horizontal plane. If I measure this angle, then this angle is called the dip angle. So first thing is the dip angle. So the dip angle is the inclination of the bedding plane of the sedimentary rock with the horizontal plane. The other thing is called the strike. What is the strike? We can go back to this photo. This is the strike. What is the strike? The strike is the line. So dip angle is an angle, but strike is a line. So strike is the line representing the cross section between a horizontal plane and the dipping direction of the rock. So strike is the line representing the intersection of the geologic structure with a horizontal plane. So this is the line representing the strike. To define this line, I have to give it an angle. What is the angle? Look here. Also back to this. This line is the line of the strike. If I measure the horizontal angle between the strike line and the north, then this is the angle of strike. So now I have an angle for dip and an angle for strike. The dip, the angle of dip, this is the angle between the bedding plane and the horizontal. The strike angle is the angle between the strike line and the north. And the strike line, as in definition, it is the intersection between the dipping plane of the rock and the horizontal plane. This figure is also an important figure that you have to understand it very good. All terms here should be understood. What is strike? What is dip? What is dip angle? What is strike angle? Where is the north? Or what is the relation between them and the north? And so on. So to define this layer, if I have this sedimentary layer of rock, I tell you, define this layer. You will tell me that this is a layer with a specific material. But what about the orientation of this layer? You will tell me that it has a dip angle of so and so and a strike angle of so and so. If you give me the dip angle, it means that this layer is inclined with a special layer. Strike angle means this dipping, is it to the right, to the left, to the north, to the south? I have to give you also the strike angle of this rock. Just as an experiment, if I have, this is the rock, and I have a bottle of water, if I put few drops of water on top of the layer, it will go into a line. This line here represents the dip of this layer. So if I measure the angle between this line of water and the horizontal, this is the dip angle. Now we go into something called the tectonic forces. This is the driving force of all what we are going to study now. Consider that you have, this is a layer of rock. Imagine this is two or three layers of rock. If I subject these 2 or 3 layers to compression, what will happen? They will be curved. If I subject them to tension, they will be stretched. If I subject them to shearing, they will be deformed. So these are the main tectonic forces that shape all of what we are going to study in this lecture. So this is the term of the forces acting on the rock. But what about the rock? Will all rock behave the same? No. Some rock are very soft and some rock are very strong. So the behavior will change. So we have two types of behavior for the rock. The first type is called brittle behavior, and the second type is called ductile behavior. If rock is very brittle and strong, and you subject it to very high force, what will happen? Similar to if you have a sample of rock and you put it in the lab. If you go to the lab, you will find many tests for breaking samples or crushing samples. What will happen when you subject a sample to compression force? It will be splitted into two parts or more. If the behavior of the rock is brittle, then it will be cracked, regardless on which level of force it will crack. But finally it will crack. And if it is ductile, then it will not crack. It will just be deformed, something like silsal, clay. If you subject, similar to this. So if you have rock that is ductile, then the behavior will be like this. Why are we studying this? Because next will be an application for that. If I have a layer like this, as I said, I have 2 or 3 layers like this, and these are subjected to compression force. If I subject it to compression force, it will be curved like this because it was compressed. But not only because it was compressed and ductile. So because it was ductile, it managed to move, to fold into folded layers without being crushed. So this is the first formation that we need to study. It is called fold. Fold is a stack of originally planar surface. So it was at the beginning planes, just horizontal layers. Then later it started to bend or to be curved after deformation. So if I have compression forces and I have ductile material similar to this behavior, so the behavior will be ductile. It will be curved, forming something called fold. So if you remember the photo I showed you at the beginning with curved layer, it means that this rock was at the beginning ductile and it was subjected to force, so it was bent. Suppose it was subjected to the force later when it was very strong and brittle, it will not fold, but it will be cracked. So the behavior will not be fold, it will be something else. So now the first thing is called fold. To define a fold, then we have to know the points of this fold or the items of this fold. We have something called the limb. The limb is the hand of this fold. If this is an upward fold or this is a downward fold, so take this upward fold, this is a limb and this is another limb. So these are as if they are the hands of the fold. And this part on top is called the crest or the hinge of the fold. And here is the trough, the opposite of the crest. This is in what you see in normal life. This is rock. Imagine that this rock was once millions of years ago just horizontal layers. But what caused all of this deformation? This deformation happened because it was subjected to horizontal compression forces, and the rock at this stage was ductile. So because it was ductile, it managed to take this wavy shape. Scientists divided folds into two types, something called anticline and something called syncline. Anticline means that the rock curved upward. Syncline means that the rock curved downward. What is the difference between the two, upward or downward? Nothing is important for us except which is the older layer. Here in the anticline formation, of course, the layer below here is the first layer that was formed, followed by the layer number 2, followed by layer number 3. The same here also. Layer number 1 was the first to be formed, followed by 2, and followed by 3. So here, the older layer is inside. So in the anticline, the older layer is inside. In syncline, the older layer is outside. So this is the definition of the anticline, and this is the definition of the syncline. By the way, it is important, and knowing which is the older, which is the newer, and what the names of each part is very important. So this figure is very important because it gives you the parts of the fold. Another thing for another photo showing the same. This is the fold. This is an upward one. This is a downward fold, and these are the layers. Of course, layer number 1 was the first to be formed, followed by 2, 3, 4, 5, and 6, and so on. This is the axis of the anticline. This is the axis of the syncline. This is just, you know it just for info. These are the types of folds. This is the normal type of fold. Imagine that this is the anticline and this is the syncline. This is the normal. So symmetrical fold is the normal type. But in some cases, folds are more complicated than we think. What does this mean? After forming this, it was subjected to more forces that affected that this axis was tilted. So if the axis is tilted, so it is called axisymmetrical fold. Sometimes the axis is not just tilted, it is deformed, it is curved. So in this case, it is called overfold, and sometimes it is much more, it is as if it was it فرمت, as if the soil was completely destroyed. So the axis is not just bent or curved, no, it was deformed. So this ends up with this shape. Imagine that this is the shape of the soil beneath the ground, and you are requested to do a site investigation. If you take a borehole at this location, you will find a very complicated structure. You will find, if the upper layer here is called layer 1 and the lower layer is layer number 6, you will find that you will have lots of layers beneath each other, and this formation is very complicated to discover with few boreholes. This is what we are going to discuss now. So now we finished what is called fold. Fold is due to structures that are ductile. But if I have rock that is not ductile, that is very brittle, what will happen? In any movement, it will be cracked. So we go to something called fault. By the way, fault is very, very important to engineers. Imagine that you have a building and this building is on top of a fault. Like when you go to a place and they tell you don't buy buildings here because this is the location of a fault. فالق in Arabic. They tell you don't live here. In this place there is a fault. It means that one day this fault may move, and if it moves, it will destroy everything on top of it. So that's why fault is very important. Fault is okay. We can put our buildings on top of a fault, because it takes millions of years to change. But fault is very, very important because the changes in a fault may happen in seconds. You may find sudden movement and everything on top of the earth is destroyed. So that's why the location of faults on top of the earth is very important. How faults happen? Look at this photo. You have layer A, B, and C. They were supposed to be all horizontal, but due to some forces, maybe this forces was tension or compression, this line E is a fault. It means that this point was here. Suddenly, it changed to be here. It moved. This point was here. It changed to go down, and so on. So fault means layers were once in a horizontal plane, then suddenly they moved down or moved up. This movement is very important, and if I do a site investigation at this location, I should be very clever to discover this fault, otherwise my building may collapse after construction, and this is it means that lives may be lost, people may die. So discovering a fault is very important. That's why are we studying all of this now? Just to know how to discover a fault. Because if I know how to discover a fault, I may save lives in the future. So this is the first definition. It's a fault. What are the types of faults? We have three main types of fault. Let's take the normal type of fault. It means that the piece of land with this tree is the original ground level. If the original ground level is here and part of the soil moves down, then this is called a normal fault. If the opposite happens, part of the soil moves up, then it is called a thrust or reverse fault. If two parts of land move horizontally relative to each other, it is called strike-slip fault. Again, some photos, but in this photo you have more information. This is the original land, and if this part moves down, then it is a normal. But if it moves up similar to this photo, then it is a reverse fault. The part that is moving up or down or away, it is called the hanging wall. So these are the important expressions that you need to understand. This is the strike slip, where two pieces of land move relative to each other. There is another type of complicated faults, which is called the horst and graben. It means that if I have, say, this is the layers, horizontal layers, they are subjected to tensile forces. With time, you will start to have some cracks here and there. With time, the cracks will widen and the part inside will fall down. So if you look at it from this point of view, it is a normal fault because this is the normal ground level and the part of the land moved down, so it is a normal fault. But if the force increases later and so on, you may have parts up and parts down and so on. So it is all called horst, and this part at the lower is called the graben. So you have to know this because sometimes this at this graben you find water coming and filling this place, and it starts to be the start of a river or the start of a sea. So these are photos of faults in normal life. You have to imagine these. This is here, person standing here. This is a person standing here, and all of this is the thickness of a layer. This layer was once at this top layer level. Then it started to move down a little bit, down a little bit, down, and every time it moves down, forming faults. Imagine that your building is on top of this area. It will be destroyed with time, of course. Now we go into something called joints. Joints is the origin of the fault. To have a fault, you have first to have a joint. What is a joint? A joint is a fracture. It is just a crack in the rock. I have a rock mass, and this rock mass is subjected to tension. With time, I will have some cracks. If these cracks, if these fractures do not move relative to each other, it's just cracked, then it is a joint. But if it moves, then it is a fault. By the way, all of these are important expressions that you have to know. So, joint, as we said, joint is a fracture without movement. Sometimes this joint is very small, and sometimes it is wide. There is a spacing between the joints, but they are not moving vertically relative to each other. But just this crack it's either a closed joint or a closed crack, or an open joint or an open crack. Suppose that this open crack has a ductile material beneath it, similar to what you see now. This was originally a crack. It was just a small crack in the rock. But beneath this crack, there was some kind of hot ductile material. With time, the material that is below here starts to move upward to fill this joint. That's why you will find something called dike. Dike is an igneous or ductile material, hot ductile material that is found below, and it just found a crack. This crack was a little bit open, so it emerged and moved to the top to fill this. So if I do a borehole here, I will find something very strange. I will find this rock, which is a sedimentary rock. But inside this sedimentary rock, if I take a borehole here, inside this sedimentary rock, I will find another type of rock. It's an igneous rock. And then I will go deeper to find, again, sedimentary rock. How come this happened? Happened because there is a dike. This is what you have to expect when you see the boreholes. By the way, I'm trying to link between geology and geotechnical engineering, and this link is site investigation. This is very important, and it is something that you are tested in the exam, how to link your geological information that you have studied with your geotechnical engineering data that you will need in your design. So if I have boreholes in all of the previous layers, how can I discover them? You know this because you see it by your eyes, but when you are digging something on top of the ground, you don't know what is below. So you have to know, you have to have the knowledge how to transfer this data into information that can help you in your geotechnical design. That's what we are going to discuss. These are different shape of dikes. Dike may be inclined, it may be vertical. This is a vertical dike, this is a vertical dike. This is filled of material coming from the bottom. This may be filled with material coming also from the bottom or from the top. It depends on, by the way, once upon a time, millions of years ago, this line was the continuation of this line. They were all the same, but what happened? There was a small crack, and this crack widened with time, and each time the crack widens, material from below comes to fill this. You have to understand what is happening. Now we are going to go to the most important part of the lecture, which is the link. We studied geology. Now we want to know how to use this geology in geotechnical engineering. As you remember in our previous lecture, when we were studying the introduction to geotechnical engineering, we said that to know the layers, we do boreholes. So, or we do test pits. Test pits are very shallow. Usually they don't give me important data about layering, but what gives me important data about layering is these deep boreholes. So I will do one borehole, drill one borehole here and another borehole here. So I will get samples showing me that this is a layer, then this I have another layer, then I have a third layer, and so on. Here layer 1, layer 2, layer 3. Usually, if the stratification or the layering is very simple, I will just pull a line between this point and this point, and another line between this point and this point, then I know the stratification. But is this what we have studied now? No. We said that I may have a curved bedding, anticline, syncline, I may have faults, I may have many other things. So I have to know from these simple boreholes what to expect in between. Just look at this. You've seen this photo before for a test pit, and you have seen this photo for the machine for drilling the boreholes, and the machine for seismic logging, where we said that this is equivalent to the ultrasound that we conduct on our body to discover what is below. We conduct the same on the soil to discover what is below. We will take now all the photos that we have studied in this lecture. Just start with the horizontal bending. If I have, imagine that I'm standing on the top and I don't know what is below. This shape is not available. I'm just on the top of the ground, but beneath me there are many layers of soil. I will just drill a hole here and drill another borehole here. The borehole will tell me that you have, this is a layer, another, and so on, and this is the same. I will just pull horizontal lines. It will give me exactly that these are horizontal beds. So in case of horizontal beds, I don't have any problem. But imagine that you have graded beds similar to the one that you have just studied. Then you will have lots of formations. You have to know if this formation, small particles, bigger particles, big particles, followed by another small, middle, a big, and so on, and this formation is repeated, then I expect to have graded beds. I go to these cross beds. In cross beds, we said that we have bedding in one direction and we have another bedding in opposite direction. Of course, this will affect the shape of the boreholes. So if I have a borehole here and a borehole there, I need to understand how to expect what is in between. Imagine that boreholes were not enough. I made this borehole and this borehole, and I'm still in doubt. I don't know, even with this ultrasound, I still cannot imagine what is in between. Then I will need to add another borehole in between, and so on. Curved beds. This, by the way, is very, very important, because look at this borehole and look at this borehole. If you look at this borehole and this borehole, you will find that the findings of both boreholes are no more or less identical. Usually, if I say that this is a layer and this is the same layer, I will just pull a line between them and say that this is a horizontal layer, which is not the case. It is a curved layer. And it may be curved upward as an anticline, and it may be curved downward also. So I need, if I am in doubt what I should do, I should add a borehole in between. Adding a borehole in between will tell me exactly what is the shape of the rock at this location. This is a dike, the same that we have said. This is a borehole. The borehole will penetrate sedimentary rock, then it will pass by this igneous rock, then it will go again to the sedimentary rock. If somebody looks at the result of these borehole, he may imagine that he has horizontal layers, and it is not the case. It is not horizontal layer. So I need to add maybe a borehole here and a borehole there, so that I can get more data about this dike. If I have a graben, as we said, that part of the soil is going down. So maybe adding few boreholes would let me understand what is happening. The same for fault, and this is the most important. It's not important because of geology. It is important because of geotechnical engineering. If you do not conduct a site investigation and there is a fault passing in your land and you do not discover it, then you should consider yourself a criminal, because you have omitted something that will end up losing lives. So this is really very important. If I do a site investigation and I find something not normal in the boreholes, I should add more boreholes, use geophysical methods, do everything so that I can get a clear definition of what is happening below in the ground. Is it a fault or not? Is the later, if I find that this is a fault, then I would have to go to a more specialized person, maybe geologist, to tell me, is this fault, is it an active fault, is it not active, and so on. And even if it is not active, I should avoid this fault. But being active or not active will tell me how much should I go away from this fault. You do not put your building on top of a fault, active or not active, because if it is not active now, it may be active in the future. So I should not put my building on top of a fault. But if it is an active fault, maybe I have to go away a few kilometers. But if it is not active, maybe I would go few meters. So it depends on the activity of the fault. So this is the link that we need to understand between geology and geotechnical engineering. This is very important. It will be very difficult for you to find it in any textbook. Usually textbooks are dedicated for geology or dedicated for geotechnical engineering. The link between both are found only in practice. In people who do site investigation in very complicated sites, and they discover faults and they discover faults and they discover abnormal structures, are very specialized in this field, and they are usually either geologists with very high geotechnical engineering knowledge, or the opposite, geotechnical engineer with very high geologic experience. So both are okay, and they have to study this situation and discover where is the problem. This ends up our lecture for today. Thank you, and see you next time.